Professor Julia Yeomans from University of Oxford. Professor Yeomans' work over the years have focused on dynamics of soft and active matter systems. And she's done a lot of work on complex fluids, liquid crystals, and more recently, she has done a lot of influential work on applying active matter models to various systems in cell and tissue mechanics. I was told that Julia very recently received one of the most prestigious awards, like the EPS Liquid Matter Prize. So yeah, congratulations.
Okay, no pressure. Yeah, thank you. Okay, so it's been lovely to be here. It's been great talking to you. It's been great listening to the lectures, and it's been great going hiking. And now I have to do some work, which is horrible. So what would make it easier is if you ask lots of questions, please, because it's always nicer to lecture. And if I don't know the answers, which is quite likely, that's fine, because that will make the next research problem. So I'm going to talk about active matter. So let's just start with an introduction, shall we, while everyone actually gets here and while we all wake up. So active matter, the idea is that these are particles, as you know, which take energy from their surroundings, and they do it on a single particle level. So why am I stressing that? Well, it's because it's not like a fluid which you're shearing, where you're doing the same thing to each of the particles in the fluid. Each of these things is an autonomous little thing, which is taking energy and using it to do work. And that's biology, right? Took me a long time to realize that, but that's actually what biological systems are doing. They're always using energy, and they're meant to be out of equilibrium. And we weren't the first, our generation, if you like, weren't the first to realize that. Schrödinger said, living matter evades the decay to equilibrium. And if you think about it, that's right? Because if we come to equilibrium, it's really bad. So let me just go through. I'm going to concentrate on active pneumatics, and in particular, active turbulence. So let's just go through some of the systems which show active turbulence. This one's just so I can show the really cute movie. This is the updated version of how motor proteins walk along a microtubule. And I did look up what these little hairy things were, and it didn't tell me. All right, so I'm assuming they're chemical bonds. Maybe other people know better. But this sort of strange way of walking is almost certainly what they actually do. I mean, that actually is based on real experiments. And these things, the microtubule and the motor protein, form the basis of the most important, perhaps, system which shows active turbulence. And that we've seen this many times. It's this beautiful setup which Zvonimir Dodik pioneered, where you have microtubules being pushed around by motor proteins. So here we are. Here are the microtubules. Here are the motor proteins, kinesin, between the microtubules. And those kinesin walk up and down the microtubules, and they have a certain directionality to them. So if they're both, and they've got two heads, so they're bridging between the microtubules. So if they all walk in the same direction, nothing happens. But if the two heads are walking in different directions on the microtubules, they push them like this relative to each other, and the whole system gets stirred up. And if you look at it, right, say this one's being pushed down, this one's being pushed up, and so you're seeing a dipolar force which is characteristic of these active systems, which you saw a lot in Kirsty's lectures. Now, what you have to do to get these things to actually do anything is make them dense enough. So you add PEG, which is a depleting agent, which pushes them together. So you've got a nice dense load of microtubules. And then what happens is that the microtubules, the ones moving up, sort of tend to end up here. The ones moving down end up here. And you end up with polarity sorted bundles which tend to move in the same direction. And then those buckle and move around. And you end up with this state which looks turbulent, like a chaotic state. Nothing to do with inertial turbulence. It's a chaotic state. And each of those sort of white stringy things you're seeing are bundles of microtubules being pushed around. And we heard about topological defects last week. You can see them already, right? Here you've got a -1/2 defect. Here you've got a +1/2 defect. But we're at low Reynolds number. Why are we getting turbulence? So that was sort of question number one. While I'm at it, again, this is really a bit excuse to show a lovely movie. Let's think a bit about bacteria now. Again, bacteria are active systems. They're driven by a more complex sort of motor protein, a more complex sort of molecular motor, which sits here and drives the tail. It's one of these rotary motors, and each of these things, which is a different color, is a different sort of protein, and these things self-assemble. And as far as people know from Richard Berry's group work, they push around the rotary motor like that. And really, I'm showing this just to show you how wonderful biology is. All right, how on earth do you end up with a structure like that, where the proteins get together and they self-assemble in something that complicated? And biology is also able to mend this if one of the rotors falls off and something tricky happens. It will be lovely to understand why you can get this sort of self-assembly. And I think many of you are actually, well, some of you are actually working on problems like that. So good luck. It's a beautiful problem. As a physicist, I always wanted a principle, but maybe it's just evolution being rather good at evolving. Anyway, if you take these E. coli and you put them together, this is a three-dimensional system. Again, you're getting active turbulence. Is it the same or is it a little bit different? Because if you think about it, right, you've got these bacteria, and if you turn off the activity, they don't form a pneumatic state, right? They just sort of get into a rather grotty heap. They just die and end up in a heap. So, you know, in the theories, we always start from a pneumatic, and then we ask, you know, what happens to that pneumatic when we make it active? But that's not quite right, because you don't start from a pneumatic, a passive pneumatic here, and make it active. So maybe that's a question we need to worry about. Then we've heard a lot about cells, and we'll no doubt hear a lot more. And I've been learning about them. And I'm just about beyond the stage where, to me, this is just a squishy cell, and they all look the same. All right. So we've got the nucleus. Here's the actin filaments that you guys are all much more expert on than I am. And the red stuff around the edge is the cytoplasm. If you take cells like this and you put them on a Petri dish in a two-dimensional layer, again, this chaotic state, again, you're seeing something which looks like active turbulence. But, you know, these things certainly are not even long and thin, right? It's even worse now, they're round. Why on earth should round, squishy things end up looking like doing active turbulence? So that's another question we've got to answer. And then I'll finish off with bacteria. These are Pseudomonas, twitching bacteria. So they work by actually using the substrate. They pull on the substrate while these little sort of hairy things which are sticking out from their sides called pili. And so they're sort of going like this. And they move forwards and backwards. So the motion might be pneumatic. It's going in both directions. And what happens is again, you get a state which looks like active turbulence. And the things I've put on there are topological defects. And this at least has the decency that it looks pneumatic when you look at it, but little blobs like this have at least short-range pneumatic order, at least the things of the right shape to form a pneumatic. So active matter, it's meant to be out of thermodynamic equilibrium. And that's what makes it different from the sort of matter that we're thinking about. So then I think we should ask the question, why is it interesting? So I've got three things, but I'm sure you have others. So anyone like to tell me why they think active matter is interesting? It's always a difficult question to ask a class because you're all sitting there thinking, actually, it's not really very interesting at all. But so why do you think it might be interesting? Come on, you're American students. You're good at talking to people. You guys work on it, half of you. Why is it interesting? Come on. Absolutely. Pattern formation and emergent behavior. Thank you. Yeah. Yeah, that's one I really like, relevant to biology. It took me about 3 years to catch on to that, but yeah, it's a new way of thinking about biology. We're very much at the stage where we don't know whether it's going to be helpful or not. Those of you that do exact models, why is it interesting then? Why is it different from, yeah? Yeah, it's a way of thinking about systems out of equilibrium. It sort of rejuvenated the field of statistical physics, non-equilibrium statistical physics. And then I had one more, any engineers among us? Yeah, these things are tiny machines. And if we could build something like that molecular motor, okay, they might be tiny, but there are lots of them and they're very efficient. So it would be great. And I think maybe the original reason for thinking about active matter is to use it as new sorts of machines. For example, you could put it in a channel and it could be a sort of self-propelled microfluidic channel. But that isn't working very well at the moment. There are lots of lovely experiments and ideas, but we don't really have enough stuff to do something like proper, industrial scale microfluidics, because these microtubule motor systems are absolutely beautiful, but there isn't much of them and they're hard to handle. So those were the ones I had. And I agree, pattern formation I'll put on next time. Anybody else got anything they want to add to that? Right. So there we are with all the things together. Are these things the same or are they different from each other? Is it fair to describe these things in terms of the bog standard theories of active pneumatics and active turbulence? So that's sort of where I'm going in these lectures. That was the introduction. And then I'm going to spend most of this lecture talking about the basics. How do we get to active turbulence? And here I'm very much building on what you've heard before, Kirsty's lectures on swimming. So I will sort of do a very quick summary of the swimming at low Reynolds number because she did it so brilliantly. And then I'll talk a little bit about pneumatic liquid crystals, just summarizing what I think is important and what I'll need. But again, this is building on what Christina said. It's the trouble with coming later, you have to do that. But it's nice because it means I can get onto the active stuff quicker. I'll talk about active stress and active instabilities. Again, that's, you will have heard some of this from Christina, but I want to do it a little bit more in detail, and then talk about active topological defects. And then we'll see how much time there is after that. And then what I want to then go on to is some sort of knobs and whistles on top of the basic bog standard theory of active pneumatics, trying to answer the questions about why these things are not just nice passive pneumatics. When you turn on activity, they become active, and they're all nice rod-like things. For example, with the cells, why are round cells anything to do with active pneumatics? So we'll move in that direction. And then I'll talk about mechanobiology. And by then, I don't know what I'm talking about, all right? And I think nobody else does, although many people in this room have their own ideas, and we all are trying between us to understand how you model collective behavior in cells. So this is very much going from what we know to what we think we know to what we don't know, but it's really exciting. So let me start off with swimming at low Reynolds number. Let me just remind you what Kirsty was saying. If I have a fluid and I have a point force acting on that fluid, or if you don't like point forces, think of a tiny colloid being pulled through the fluid with a force F. And then let me ask, what's the velocity field set up by that force? And the answer is the Stokeslet. Stokeslet you saw in Kirsty's lectures, and it looks like this. Velocity proportional to the force. That's because we're at low Reynolds number. So we're looking at the Stokes equations, and the Stokes equations are linear, which is good because we can do things with them. And then we have force over 8 pi. This is the viscosity, I over r. And the important thing is that the velocity field goes as 1 over r. So if you look a long way away from the swimmer, you have a velocity field, a far flow field, which goes as 1 over r. Actually, deriving this is quite tricky, not really hard, but it helps to look it up because it's a long proof and you have to go in the right direction. See, for example, Doy and Edwards. But if I have a swimmer, that won't work, right? If I put a force on the swimmer, you can't do it because we're not all sitting there pulling these swimmers around. And so there can be no net force on the swimmer because these are self-propelled particles. So we lose that 1 over r far flow field. And what we're going to pick up instead, we can't have this force, is a far flow field which goes as 1 over r squared. And we might guess that that's due to a force distribution which looks like this, equal and opposite forces acting on the swimmer. So what does the flow field due to that dipole set of forces look like? So let's draw it here. Okay, so now I have a swimmer. To a good approximation, I can take my swimmer, I can approximate its far flow field is due to these equal and opposite forces. And what you end up with is a picture which looks like this. Very different symmetry, yeah? For example, here's my swimmer. It's pushing fluid out from its ends and it's pulling it in from its sides. What's the symmetry of that thing? Yep, come. Sorry? Dipolar or pneumatic, yes, right? Got a special direction, but it's the same forwards and backwards. Remember that I'm talking about the far flow field here. I'm talking about what happens a long way away from the swimmer. If I want to worry about whether this thing actually swims or not, that depends on what's happening around here, the near flow field. And then you have to worry about the scallop theorem, which says that the swimmer's stroke must be non-reversible in time in order for you to actually get swimming. So it's a bit confusing thinking of swimmers actually swimming somewhere, but then talking about a long-range dipolar or pneumatic field. And that's because what we're worrying about here is the far flow field, what happens a long way away from the swimmer. You all know this because you did Kirsty's problem, yep. This is 3D. Yeah. Yeah, this is 3D, that's right. Okay, so I'm sure you all did Kirsty's problem, which said let's actually work out what that field is, all right? So you look at the Stokeslet due to a force like that, and you add a Stokeslet due to a force like that, where these two forces are a distance L from each other. And you can do that because R1 is approximately equal to R and R2 is close to R. So you can do a Taylor expansion on that. I'm sure you all did it. And what you end up with is a velocity field which looks like this. Does it make sense? Well, yep, 1 over R squared. That's what we expected. It has an angular dependence, which you have to do the calculation to find out. And then up here, force times the distance between the forces. That's like a dipole moment. So we have a dipole strength for this field. So swimmers to leading order a long way away have dipole flow fields, and that's because they have no net force acting on them. This is the famous picture. I'm sure you've seen this before. Beautiful picture of a real swimmer with a real pneumatic symmetry dipolar far flow field. That was really, really difficult experiment to do because you can't just sit and look at a swimmer and that's its flow field. What you have to do is look at about 500 swimmers and then average, put them all moving in the same direction and average. And what you end up with is something which looks like that. Beautiful experiment, which really shows how this works. I put that up, make absolutely clear we got this straight. This is really the point. This flow field has pneumatic symmetry. And that's why we call these things active pneumatics. And it's why when we're writing down the equations for active pneumatics, we start with the pneumatic order parameter Q. This is just words, okay? If the flow field goes like this, out from the ends and in from the sides, it's called extensile. Swimmer people call it a pusher. Got you. This one is contractile. Yeah, sorry? That's a complicated question. It depends where they are relative to each other, exactly how they align. And it depends whether they're extensile or contractile. Yeah. In the far field, a long way away, I think they probably do align, but the minute they turn like this, what happens is they go towards each other or away from each other. So it's not a stable state. That is a calculation that's been done, and the answer isn't totally trivial, but you can sort of look it up. Yeah. Yeah, other questions? Right. So that's the important thing about swimmers. Let's just think a little bit about pneumatics. We went on holiday about a month ago. First thing I saw was a cushion on the sofa, which was a pneumatic cushion, right? Nothing like being reminded of work when you're on holiday. So you heard about this from Christina. Here's my pneumatic. Everything is pointing in more or less the same direction. So this is really quite strong pneumatic ordering. There's long range order in the direction of these things, but there's no long range order in the position. And that is a pneumatic state. We need an order parameter to describe it. You can either describe it with a director field. A director field is just a headless vector, which is pointing along the direction. But that doesn't tell you how ordered it is. It only tells you which direction it's ordered in. And so you can do much better with the Q tensor that Christina introduced. So the best order parameter for these pneumatics is the Q tensor. The Q tensor is a traceless symmetric tensor. And what's the reason that it can describe what's going on in these systems is that its largest eigenvector gives you the direction that the pneumatogens are pointing, and its largest eigenvalue tells you how ordered they are. We can just look at this and see why it's a symmetric traceless tensor. This I and J are Cartesian directions, so those just label the Cartesian directions. It's obviously symmetric because if I switch I and J, I end up with the same thing. It's traceless because I subtract this term here. So let's look at QXX squared plus QYY squared plus QZZ squared. That's going to be NX squared plus NY squared plus NZ squared. But this N is a unit vector, so NX squared plus NY squared plus NZ squared is equal to 1. And then I have delta XX plus delta YY plus delta del Z, 3. This is the delta function. 1 minus 1 will give me 0. So it's constructed to be a traceless tensor. So this is what happens when you heat up a pneumatic liquid crystal. When you cool it down, really. At high temperatures in the summer, right? Nothing is pneumatic, everything is random. At low temperatures in the winter, this thing gets aligned. It can change to a pneumatic state either through lowering the temperature or by putting in more pneumatogens, so these things are more organized. Stop me if I'm going too fast. I'm going fairly quickly because you've seen all this before from Christina. Yeah. Okay. So this system can have small and unimportant defects, right? If there's a small change in local change in the direction, there's an elastic energy associated with that, and very easily it's just going to relax back so that everything is aligned again. This thing is elastic, it's an elastic liquid. You can also have much more important defects, and these are these topological defects, and I'm in 2 dimensions now. This is what topological defects look like in 2 dimensions. They're called topological defects because they distort the director field all the way to infinity. There's no way you can untwist that without doing something on the boundaries at infinity. And so because they distort the director field all the way to infinity, the energy of each of these things is going to be infinite. So you can't actually have a plus or half defect on its own in a perfect infinite system. You can, however, have them in pairs, plus or minus a half pairs. And what they will do in a passive system is gradually, to lower their energy, they'll move slowly towards each other and annihilate, leaving you back with a perfect pneumatic crystal. And that's a good thing because if, you know, these things are what you have in a laptop. In your laptop, you have a pneumatic, and you really don't want topological defects in there because it's going to muck up the purity of your laptop screen. So remember the shapes of these things. The plus a half looks like a comet, and the minus a half has this threefold symmetry. In a passive system, they would just tend to annihilate with each other. Now, we need to write down, the other thing we need to know about passive liquid crystals is the equations of motion for these things. Okay, so sorry about this. Well, I'm not sorry about this slide, okay? But they're not going to be many like this. And I don't mind doing this because really it's not super important for what we're going to talk about. It's not important at all for what we're going to talk about. The punchline here is that we understand how to write down the equations of motion, the continuum equations, so like the Navier-Stokes equations for passive liquid crystals. All right, and I'm going to take you through it just to give you an idea of what all the terms mean, but there's no way you're expected to know exactly what horrible things like that are doing. You just have no, if you ever want to use this, go and look it up. So I want a Navier-Stokes-like equation, but I want it for a structured liquid. So you need an equation for the velocity, but you also need an equation for the order parameter Q. So how is Q going to evolve in time? Well, first of all, Q is going to change in time and also change locally because it's being vectored around with the flow field. So this is the normal total derivative, which tells you how Q evolves in time. Then this S thing here happens because of the shape of the molecules. A liquid crystal molecule has this shape. So every time there is a shear flow in the system, right, shear is going to do that to it, it's going to turn in shear flows. So we need a term in there which couples gradients in the velocity with the order parameter. And it's a horrible term, but people understand it. It's this S term here, okay, where I have gradients in the flow. Here I have the symmetric part of the velocity gradient tensor, and here I have the antisymmetric part of the velocity gradient tensor. Okay, so nasty term, which takes account of the fact that shear flows will turn these liquid crystals. This lambda, we will think about a bit later. It's called either the flow aligning parameter or the flow tumbling parameter. All right, they're exactly the same thing. And what it does is it just says, what's the relative response of these things to straining flows or to rotational flows? As lambda changes, the relative importance of flows which tend to pull things like this and ones which tend to turn it change. And lambda is a parameter which just depends on the shape of the nematogens that you're worrying about. So then if I turn off the flows, what's going to happen to this thing? Well, it's going to relax back to the minimum of a free energy, okay? And we know that liquid crystals are described by the Landau-de Gennes free energy. Christina's talked about this quite a lot. Landau-de Gennes free energy, you have an expansion in the order parameter, which you always do with these Landau expansions. So there's an expansion in the order parameter Q. And then I have this elastic term, which says that the thing doesn't like being distorted away from its aligned state. So what I need in my equations is something which says that if I turn off the flow, it will relax back to the minimum of the free energy. And that's just this bit here, gamma, which is a rate constant, times h, which is basically df by dq. And this is just model A dynamics, just straight relaxational dynamics. This thing is relaxing back to the zero of the free energy. Okay? So that's the equation for Q. I also need an equation for U, the velocity field. And the way I've got it written there is just like Navier-Stokes. Yep. This side is the usual inertial term. This side is the derivative of the stress tensor. And we all know about viscous stresses, the normal viscous stresses, just viscosity times velocity gradients. And what makes liquid crystal different is a rather nasty additional stress term, which is bunged in here. I've called it here the passive stress or the elastic stress. Got the pressure in. We know about that from Navier-Stokes. Then it's got all these horrible things which couple the free energy and the order parameter. Don't worry about those, they're horrible. And luckily, they don't actually matter much because it's usually a very small effect. But physically, what's going on there is that if I have flows, they're going to turn my liquid crystal. Sorry, wrong way around. It's the other way around. It's the Q, right? So if I have an order parameter like this, if I have a molecule like this, and it starts turning, it will induce flows. It will induce a stress in the fluid, okay? So my Q tensor, my nematogen as it turns, will set up flows. They're called backflows. They're not usually very important, but if you're a liquid crystal technology, if you're designing display equipment, then they're important, because what happens as you switch liquid crystal displays, switching them means that the molecules have to turn to go from the on state to the off state. And what you'd like them to do is just turn quickly and then stop, so you have a fast switching time. What actually happens is that they go a bit too far because of these induced flows. As the thing's moving, it's inducing flows, and then it takes them a while to relax back to where they end up. It's called the optical bounce, and getting rid of this optical bounce is very important if you're into display technology. Okay, so that's the important bit of those two rather nasty slides. Yeah. Mm-hmm. I think the coupling between the active stress, I mean, at the moment, it's not turbulent. These are passive equations, yeah? So what's going to give us active turbulence is the active stress term, which is what is coming next. And then the active stress is an extra stress, so extra forces on this fluid, which couple in with the pneumatic order parameter. This one is not important, thankfully. That one is not important. You need a viscosity to get things to work. I think every term there is important. Yeah. Mm-hmm. Actually, oh.
You compare this to previous simulations, do you need millions?
I mean, for just straight Navier-Stokes, you can do it amazingly small. So something which is nanometers can often be described by Navier-Stokes. This one here, it works very well, actually extremely well, for just the sort of pneumatic liquid crystals you have in your display thing, where presumably microns, it's absolutely fine at microns, and I think even down to maybe 100 nanometers, it would be pretty good. The extra thing there you'd have to worry about is fluctuation. So you'd need probably fluctuating version of this. Yeah. Other questions? Right. So what we're trying to do is describe active turbulence. We're going to take those equations as understood, and we're going to think about active turbulence. Active turbulence. Okay, this is two-dimensional swimmers now. And what I've plotted here is the vorticity field, right? Vorticity is how much this thing turns. So the red bits are anti-clockwise vorticity, and the blue bits are clockwise vorticity. And typically, you'd have maybe about 10 or 5 swimmers across one of those vortices. So active turbulence is a highly vortical state. We want to take the liquid equations and we want to do something to them so they'll describe active turbulence. What's extra in this system that wouldn't be there in a passive pneumatic? That's what we've got to ask ourselves, yeah? So what's extra in this system? Well, anyone want to tell me what's different? What makes it active? Sorry, yeah, active stress. Let's go back one step. What's causing the active stress? I mean, you're absolutely right. Yeah? Yep, exactly. That's sort of step one. They're moving. So they're creating a flow field, which is giving an active stress. That's what's different. That's what we have to put in. We have to put in the flow field due to each of these things. And we know at least what the far flow field is. Okay, we know the symmetry of the far flow field. It's like if you're in the bath and you've done this and you sort of squish up and down, right? The fluid around you moves and it's fun because you can get it to come over the edge. Exactly the same story. So what does that flow field look like? The flow field that we've got to put in? Well, we know that because we've worked it out. There are questions about whether it's okay just to use the far flow field, but typically we're doing a continuum theory here. So we're coarse graining and we're looking at the sort of the leading order, the most important long wavelength perturbations. So we have to sort of take it as read that the far flow field will be good enough. So this is the physics we're putting in. How do we put it in? Well, it's actually dead easy. All right, luckily this is the easy bit of the equations. What you have to do is just put an additional term in the stress. So here's the stress. Okay, it's under a derivative. We expect that additional term to depend on Q, because I've gone on at long length about this far flow field being pneumatic and having pneumatic symmetry. And it just looks like that. Okay, the extra bit of the stress, the active stress, is minus zeta times Q. There's several ways of getting to that. The first one is clever guesswork. Basically, we know it has to depend on Q because of the pneumatic symmetry. How can you put a term which depends in Q into these equations? Q has two indices, so just to get the index counting right, it pretty much has to go under the stress. Okay, so people who are good at guessing these things would immediately be able to guess that. Q is the order parameter. This zeta thing is just the strength of the activity. It tells you how many swimmers you've got and how energetic each of them is. Okay, the sign here is negative for extensile systems and positive for contractile systems, unless you come from Santa Barbara, in which case it's the other way around. But basically, we just have to worry about them being different signs. It's just changing the sign here, which moves you from an extensile to a contractile system. It's not too hard to have a sort of hand-waving version of how to get this, starting from a load of pneumatogens and adding up the far flow field from each of them. And that is the problem that I've put on my problem set if anyone wants to do it. And it's also done in a paper by Simha and Ramaswamy, a very famous paper, about 20 years old now, which derives this starting from a more microscopic state. And I'm going to show you a picture about how that works, but leave you to do the maths. It's maybe half a page. Look it up and see if you quite believe the derivation. I mean, it's a very, very clever piece of physics, but if I was a mathematician, I might worry a bit. Yeah. Of course, I love top quiz. Just because of the symmetry, or let's do the easiest thing first, I think. Yeah, I mean, sure, there are going to be extra terms on here, okay? And people are worried a bit about the extra terms you could possibly have. So it's really the easiest one that we're putting in there.
So especially the microswimmer swimming and not actually in the near field.
Yes. It is a far field argument, yes, and you could argue about that. And if it didn't work, that's one of the places you'd go back and look at it. But it's a very valid question, yes. You can have higher order in Q, or you could have derivatives of Q. As long as you have the right number of indices, you can put what you like in there, okay? And then you sort of say, well, this is likely to be dominant, all right? Because usually Q is smallish. You can say that, and then you can. Ooh. People have done theories with additional terms. I don't think there are experiments which have really definitively shown that the other terms matter. I may be missing something, but I think that's true, yeah. No, not an important change. Again, there are terms you could add in which are active terms, but they can actually be subsumed in the Landau coefficients. Yeah.
Maybe a silly question, but if these things are moving in a certain direction, why is pneumatic symmetry appropriate?
No, I mean that is absolutely a sensible question, and it always sort of worries people, right? We're doing the pneumatic symmetry is appropriate because the far flow field is pneumatic. What we're doing here is coarse graining over lots of these things. So we're hoping that what happens locally is not important. And one way of thinking about it, I think, is that even though each of these little swimmers is moving in a polar sort of way, we're always looking at lots of them. So when we average, there's no net polar direction. Yeah. And indeed, even if you look at polar particles and then try and work out what's going on, the hydrodynamics needs a term like that. Yeah, but people have worried about that. Yep. Yes. It's a bit like if you're doing Navier-Stokes, you stop worrying about interactions between molecules. Yeah. Similarly here, when you're doing this, you're stopping worrying about short-range interactions between swimmers. You're looking at the generic long-range behavior when you're looking at these continuum theories, okay? So you have to ask the right question. But you can use Navier-Stokes for pretty much any sort of fluid, yeah? Until you start, any sort of simple fluid, yeah? And so what really matters is the symmetry as much as the interactions. So it's that sort of description that we're using here. Yeah. Mm-hmm.
So here the active term is added sort of by hand to the stress, but like alternatively, one could say, let me write down the most general field theory, dynamical field theory allowed by symmetry, allowing for terms that don't come from free energy, the same way one does for like active model B or B plus. I'm just wondering, like, is this the lowest order term that you would get, or
yes,
should you treat this more normal?
It's the lowest order term that you'd get. Yeah. Yeah. And there are slightly more. In the end, this is a symmetry argument. And in the end, these continuum theories are symmetry arguments. But there certainly are higher order terms you can worry about. Yep.
Doesn't the viscous and active terms also have linear QID?
They don't make any difference to the physics. Okay. Well, let's see. Let's see. Okay, but this, before we see, I'm going to talk a bit more about this. Let's just do the punchline, shall we? In terms of understanding behavior of these things, what you have to notice is that this term comes in the stress. So it comes under a derivative. I have a derivative of Q. So that means that any time the order parameter changes, its magnitude changes, the direction of the pneumatogens change, you have an additional stress, and so you have flow. Okay? Gradients in the magnitude or direction of the order parameter, or actually also in the strength of the activity, will give you a stress, and that will give you forces and flows. So that's what we had before, right? That was a passive system. This was a nice little distortion in the passive system. Yep, and it just relaxed back. But this is a change in the order parameter. It's a change in the direction of the order parameter. And so what's going to happen is you're going to get stresses and you're going to have flows. If the flows are going this way, that's fine. It'll just relax back to equilibrium. But in fact, in an extensile system for this one, the flows are going this way. And so what happens is that this system is unstable. These tiny distortions just get bigger and bigger. You saw the idea of linear stability analysis in David's lectures, right? This is the same story. And the stable pneumatic state is destroyed, and you get something else. The something else, you can't tell what it is from linear stability analysis, but you know it's something else. Let's do that a bit more carefully. Same thing. See how these flows balance each other. So the black things on my slides here are those little pneumatogens. Yeah, these things here are the nematogens. Let's have them being extensile, so they're pumping fluid out from the ends and in from the sides. And here I've got a lovely state of perfect pneumatic order, so a load of swimmers like a load of soldiers moving along. So what's going to happen is here, okay, these things are going to balance. The flow field is going to balance because the flow out of the end of this one will balance with the flow from the end of that one. Similarly for the sides, it's going in on each side, and you can see that if I put in all the blue arrows, everything's going to balance. The far flow field will balance out, okay? And so nothing is going to happen. So now let's have a tiny little fluctuation. We'll have a bend fluctuation in these nematogens. So it's bending like that. And again, I'll put in the flow field. Well, the flow field between them is still going to balance, but the flow field coming in, if I put my arrows in, looks like this. And the strength of the flow field is going to be larger here. The more arrows, the arrows are close to each other, that means the flow field is stronger. And so I'm going to have a net flow in this direction. You couldn't just have that with an incompressible fluid. So if you look at this bit, everything balances nicely. Here, what's going to happen is the net flow is going to be in that direction, and you're going to have stronger flows from the top and weaker flows from the bottom. So what you end up with is vortical flows in this system. This thing goes round in a vortex, which is one way of sort of thinking why these things end up with a lot of vorticity in them. And one of the problems is now draw the same picture for contractile ones. In contractile ones, it's splay instabilities. It's splay distortions, which give you instabilities. Yep.
So it seems like you could just rotate this by 90 degrees and switch extensile to contractile, and then it would be the same. What's the use of distinction between them, and how in the equations are they?
In 2 dimensions, you can actually map one onto the other. Okay, and you're okay. And the reason is that bend and splay don't exactly map onto each other. So beyond the linear thing, there is a bit of a difference between them. So that's why it's good to distinguish. In the equation, you just distinguish by that minus z to q thing. It's plus or minus z to q. 3D, it's very different, okay? Because in 3D, if you think of a long, thin thing, right, you have one extensile direction and lots of flows going in directions. But if you make it contractile, you have one flow going in and lots going out. So the mapping doesn't work in 3D. But yeah, go on.
I see how the
I think you'll find that splay and bend are not. I'd have to think a bit about it to know exactly what, but they are very close. And I think in 1D, you can actually do an exact mapping. I think it's that way around. But where we're going to get to at the end of these lectures is that talking about extensile and contractile gets very iffy if now instead I have squishy cells. Yeah.
This wave-like form,
Mm.
you have extensile dipoles placed at the nodes of the wave, we are going to enforce the instability, which maybe I can argue along that lines. But what happens if they are not placed on the nodes of the instability, rather on the anti-nodes? They will
So where's your antinode?
yeah,
Here, you mean?
Yeah, so you have extensile dipoles, but this is like a sine wave.
Yeah.
Putting them on the nodes.
Well, look, I mean, these will happily balance, these guys, with those up there. So that if I have it straight and parallel, they'll balance beautifully. So it's okay. And then this one here will push up and that will push down. And so you'll increase the instability. I'll draw it for you afterwards if you're still worried. Yeah, other questions? Okay, and then one of the things we're going to talk about later is the idea of an active length scale. This is the length scale of those vortices, and just a hand-waving argument about what it should be like. The length scale is determined by a balance between the activity and the elasticity. Okay, I'm just telling you that, but it sort of makes sense, right? You've got the activity trying to impose bend and splay distortions on these things, and you've got the elasticity trying to pull them back to not being distorted. If you look at the units, you can immediately see you've got a length scale here, and the length scale is root k over zeta. Okay, that is a typical length scale for these active systems. So that's where we're up to. Please, can you remember that? Because again and again, I'm going to be able to say we've got gradients in the order parameter, and that's why we're getting these sorts of flows. You can explain almost anything with this idea that gradients in the order parameter give you stresses, give you flows. We've done linear stability analysis, okay, at least pictorially. We know that the ordered state, the ordered pneumatic state is unstable. What do we get instead? And to answer that question, we actually have to solve the equations, and then you go and take your favorite computer program and you solve those differential equations, and let's see what happens. And what will happen is active turbulence. So this is the experimental picture we've seen. If I solve the equations and plot the velocity field, it looks like this. The yellow things are regions of higher velocity, and you can see you tend to get these jets of velocity. And then this thing here is the vorticity field, and I can't actually remember whether I've taken that from an experiment or from simulations. They really do look pretty much the same as each other. Yeah. Essentially, yes. It's either the scale of the vortices or the same thing, the scale between the defects. Yeah. So it's essentially the scale of anything that's going on in that system. Yeah. These things normally flow aligning. I can't remember exactly what the value that gives that. I think it's greater than 1. So I was trying to help with what flow aligning. Which one is it? Greater than 1, yeah. Mm-hmm. With molecular liquid crystals, they are normally flow tumbling, I think. Yeah, with these big ones, you'd expect them to be flow aligning. But people have no way of calculating that. You actually have to look at them and see what they're doing. I mean, it's complicated. We know for a single nematogen whether it aligns with the flow or whether it turns in the flow. But here you've got lots of them. And then the short-range interactions are important. So it's a thing rather like viscosity is really hard to calculate, yeah, because of all the interactions. Flow alignment, it's the same story. Right, so what we're going to do now is just take a microscope and look at this picture from simulations just to see what's happening on a shorter length scale. Right, so there we are. So we're just sort of going into that little patch there. And what you can see in particular, we're doing it again here. Now I'm showing these things now are, these are the flow lines, the black ones. The colors are the vorticity, and we're starting to see the individual nematogens here, the individual swimmers, if you like. And the point to notice is that there's a very obvious bend here in the nematogens. The bend in stability has grown. Here, the order parameter is obviously changing direction pretty quickly. It's changing direction very quickly. And so what's happening is it's pumping fluid down here. So that all sort of works and it all fits together. Yeah. Hello, did you have a question? Please do. Yeah, do ask, because it's great. Very sensible question. Sorry not to explain properly. It's the vorticity, the color scheme. So the red ones are one-way vorticity and the blue ones are the clockwise one. No, it's the strength of the vorticity. It's essentially how fast it's going around, the strength of the vorticity. Yeah. Other questions? Yeah.
Now coming question about system size.
Mm-hmm.
Somehow now if I see the structures, okay, I would assume the molecule should be one of them, the base structure, and then I have the strength scale, and the system size has to be larger than this, otherwise I don't get the structure evolving. So this must be sort of a minimal system size I need for this to work.
Yes. What we're going to do next lecture, or one lecture, is we're going to take this stuff and we're going to confine it. And if we confine it to a shape which is that sort of size, which is smaller compared to a vortex, you lose the active turbulence. So what do you get instead? But that's sort of a physics question, slightly different than a question about when you can use continuum. You can use continuum even on a smaller length scale, because then it's the length scale compared to individual, in this case, swimmers, and maybe 100 by 100 swimmers would easily be fine. Yes, the nematogens, you need, this tends to be about 5 or 10 swimmers, and that's really a minimum you can have. Yeah. Sorry, yes, this is the director field. Yeah, think of it like that. The flow field is what you get. Yeah, the flow field has nothing to do with the swimming direction of the bacteria. Perhaps you should think of these things as lots of bacteria because we're doing it coarse-grained. And so the swimming direction of these bacteria will be lots of different directions. Yeah, but on top of that, the flow field that they will be producing on average is these things here. Yeah. Yes, but the things which is producing the Stokes-Lutz are really pretty random by now. Yeah, thank you for the question. That's lovely. Yeah. Yeah. That's a consequence of we're doing the simulation on the grid. Yeah. And so, yeah, okay, it's just because of the simulation. Yeah. Okay. So we've got active turbulence. We've got a pneumatic, and so we expect topological defects. So what we did next is take the simulation and we found the topological defects and we put a red blob every time there was a plus a half defect and a blue blob every time there was a minus a half defect. And then we ran the simulation, we asked what was happening, and these things, let's see if I can get one which works, do as they're meant to do. They annihilate each other, plus or minus a halves. But then if you look up here, whoops, you also get them appearing. So what makes this thing very different from a passive system is that topological defects not only annihilate in pairs, they also appear in pairs. And that's okay, because it's an active system. So we've got energy, we're pumping energy into this system. And so the energy gives you enough energy to overcome the energy barrier you need to create a pair of defects. Can happen in a passive system too, due to thermal fluctuations. But what happens in a passive system is they might be created, but immediately, because they're close to each other, they destroy each other again. Here what happens is that the minute they're formed, the plus ones move away. The plus ones are self-motile, so they're able to escape and move around till they find another -1/2 defect somewhere and annihilate. So you end up with a gas of topological defects. So you can watch them again, moving around. It's up here. It's the one I usually look where they actually appear. And so you get, on average, a fixed number of plus or -1/2 defects. If this thing is more active, you expect more defects to be produced. Okay? Yep. +1/2 defects move, -1/2 defects don't move. When I say don't move, I mean they're still moved by the background flow, but they're not self-propelled. So that's a good question, because that was the next comment, which, why are these things self-propelled? Okay, well, you know that because it's obvious that there's a change in the order parameter. Change in the order parameter gives you stresses, gives you flows. Okay, so there are going to be stresses on this thing, and it's going to move towards its head. If it's an extensile system, if it's a contractile system, what happens is that this thing moves towards its tail. It's not obvious about the direction, but it's fairly easy to work it out. This one, you also get changes in the order parameter. Yep, changes in the direction. So you certainly get flows set up around it. But because of the symmetry, because of the threefold symmetry, those flows balance. Okay? And those flows balance, and so it's not self-propelled, but it still is moved around by the background flow. Christina and I disagree about these defects a bit. I mean, she said that you can take this thing and you can write it down as a gas of topological defects, and then you can write down a theory in terms of these things being sort of quasi-particles which move around. I don't think you can do that. I think the defects in the flow are so coupled to each other that you actually get a bit stuck doing that. But, you know, she might be right, I might be right. I think there's still a question about that. Let's look at these topological defects and the flow around them. Okay, just to, sorry, I like this, so see this lots going on. Yeah. Sorry, we won't do that just yet. Going back to experiments now. How are these defects formed, you know, in a real experimental system? So this is the microtubule motor protein system, all right? Microtubules bundles are sort of these thread-like things you can see here. These things buttle, and as they buttle, you can see that, you know, the buttly bit sticks out further and further. And then if you look at this in terms of defects, this one here is a +1/2 defect, and this one is a -1/2 defect. The flows are pushing them like this, +1/2, -1/2, +1/2, -1/2. And so what you can see is that they are formed in pairs. Physically, what's happening is that the microtubules are buckling, and then they're moving away from each other. The -1/2 is staying in one place. I guess you have to believe me that these pictures are not moved relative to each other. And the +1/2 is moving off like that. Good, so it sort of works. The continuum theory, where you can't see exactly what's going on a microscopic level, fits when you can look and see a bit better what's going on in a microscopic level. The green dots are +1/2 defects. What do you think the difference is between that one and that one and that one? Yep, exactly, right? These guys are being better fed. Let's see the movie. More activity here, so you can get more defects. The length scale was root kappa over activity. Larger activity, smaller length scale. Defects are closer to each other. So that all works. Yeah. You tend not to, no. Lambda doesn't really make much difference in these systems. I think because it's so chaotic anyway. So they're all moving around in the vortical flow. So the exact value of lambda normally is not very important. It's very important in some systems, but not here. Okay, this is what I thought came next. Okay, so let's actually look at the flow field around these defects. So this actually compares some calculations from a paper by Luca Guillaume, which looks at the flow field around -1/2 defect. Remember, we had that threefold symmetry. Here's the flow field. It has these lovely vortices appearing. Here's the flow field around a +1/2 defect. You just get 2 vortices in the flow, and the defect pops off in this direction. So that's an extensile defect. Just to prove that it's sort of okay, these are the flow fields around defects in this bacterial system that we saw earlier. And these are the experiments. The experiments, of course, are not wonderful because this nasty, I mean, the experiments are wonderful, but the system isn't wonderful because of the very loads of fluctuations. So it's much, much harder to see what's going on. But you can pretty much see the same sort of story, right? 6-fold vortices around the -1/2 defects. And here you get 2 vortices around the +1/2 defects. Yeah, good. I do. Because we are looking at a continuum theory where we put in the basic symmetries. Yeah. And so the sort of the most important features are going to be the same. And then you can ask, well, you know, is it quite the same? Yeah. Yes. Well, you wouldn't really with swimmers, actually, because quite what a Frank constant is for a swimmer, I think is a question. Yeah. I mean, you're right. This is a continuum theory. And so quite what to put in for the parameters is a big question. Yeah. Yeah. I mean, people have tried to do more microscopic versions of this when they actually look at active filaments, and then they'd be able to answer that question better. And I'm not sure where that's up to, but at the moment it's just a parameter. And yes, it will change between different systems. I think 100 microns. And they're fairly long and stiff, aren't they? Other people know this much better than I do. Okay. Is it? Sorry, I'm.
They're not. The whole system freezes when the motors are turned. It can be an active pneumatic, but then it's not. And it's very cross-linked, and you can see those density fluctuations. I mean, it's like it's an active pneumatic elastic. I mean, that's what not a pneumatic, and it creates something that's like definitely. But
yeah, no. Yeah. And indeed, one of the things I'm going to talk about next time is exactly part of that point. But when you turn off the activity, you don't get a pneumatic. So, you know, does it matter in that system? And also in the bacteria, because they all sort of die and end up in a clonk on the floor, you don't get them all lined up beautifully in pneumatic, right? So we have to worry about that. You can do that, yes, yes, yeah. But if you actually turn it off, you know, you don't start from the pneumatic state. Yeah. And you're quite right to worry. Yeah, yeah. You want numbers? Oh, help. If you look, as a theorist, what I could say is that if you change K within reasonable bounds, these things look pretty much the same. The shape of the defects changes a bit, but the active turbulence doesn't change. So probably the value of K doesn't matter too much, at least for this sort of question. Yeah. Yeah. The microtubule motor system is usually at an interface, I think, between water and oil. So it goes to an interface and it sits at an interface. So that's what makes it two-dimensional. Yeah. In our simulations, they're just two-dimensional. Yeah, yeah. The bacteria, usually they're sitting on a, well, you know better than I do, sitting on a surface, I think, just swimming around. And it really doesn't matter whether you're 2D or 3D, the active turbulence is very similar. Yeah. Right. So that sort of got to the end of active pneumatics. And that's just a couple of things which might be interesting to read. This thing here has a very short article on lots of things to do with active systems. Each of them's got 4 pages with 10 references, and it's a lovely format if you ask me. So if you want to learn about something, where to start, I think this roadmap is a nice place to look. I wasn't quite sure what I was going to do next, but I think given the time, what we're going to do next is just very quickly look at 3 dimensions. 3-dimensional active turbulence is not very different from 2-dimensional active turbulence. The ideas are the same, but of course, the topological defects are different. And again, it was von Dogic that was the first person to look to design experiments where they looked at this microtubule motor system in 3 dimensions. And of course, in 3 dimensions, it's very, very much harder to actually image what's going on. With the bacteria as well, I showed you a 3D picture, but again, that's really quite recent because of the difficulty. It's much, much harder to image things in 3D than 2D. And for theorists, that's great because it's so much easier to do the simulations in 2D. So this again is the microtubule motor protein mixture. Okay, the difference, I mean, what Zvonimir had to do to get this to work is that he had to add a background of passive pneumatic colloids. And that's to get these things pneumatic enough that they would give you active turbulence. You needed the background pneumatic to help the active pneumatic align. This is the movie which shows the topological defects in these systems. So in 3-dimensional liquid crystals, rather than having point defects, one has line defects. So you get lines. These lines have to form loops, so they can appear as loops, or they can join with each other. They can split, but you can't have free ends except on surfaces. They just shrink back to a pneumatic state. So this is a lovely movie just showing these loops appearing. This is an experiment. Simulations give exactly the same thing, but these are real experiments. Here are the loops. These are defect loops. The white things are the direction of the sort of pneumatic background. And everything's much worse in 3 dimensions. Just got a a couple of slides on this just to tell you a little bit more about what these disclination lines look like in 3D. So imagine a disclination line, which is meant to be the line across my slide. And then what I want to look at is the pneumatic director configuration on cross sections of that line. But it's a bit hard to draw those. So what I've done is sort of turn them round a bit so we can see what's going on. If you look at the cross section, you can either see things which look exactly like a -1/2 defect, something like this. All right, so this would be a -1/2 defect if you pretended it was 2 dimensions. You can see things which look like a +1/2 defect. So it makes sense, right? Where the nematogens are all sitting in the plane. And then you can also get these new things, which are called twist defects, where the nematogen twists out of those 2-dimensional planes and points in the 3rd direction. And the real difference is that whereas in 2 dimensions, ±1/2 defects are topologically protected, that's a fancy way of saying they can't change into each other. In 3D, what can happen is that a +1/2 defect can twist out of the plane and turn into a -1/2 defect. So the thing which is topologically protected is the whole loop, but around the loop, you can have bits of +1/2 and bits of -1/2 and bits of twist. And what actually happens, sorry, this slide is probably a bit much actually, so don't worry too much about this one. What actually happens in these systems, in an active system, is that if you have an extensile system, you tend to get twist defects. So this says this is the probability of different sorts of defects. The ones in the middle are twist defects. The one at the edge are ordinary ±1/2 defects on the cross section. What this is saying is that in an extensile system, you really tend to get these twist defects with the nematogens pointing out of the cross-sectional plane, whereas in a contractile system, you don't. You tend to get them being ±1/2. And the reason for that is the flows setup, the active flows setup. In an extensile system, if I have a load of nematogens in a plane and I allow flows, they're unstable to pointing out of the plane. If I have a load of nematogens in the plane and I allow flows in the 3rd direction and I allow them to flip out of the plane, contractile ones don't want to do it, but the extensile ones do want to do it. And that's something which really hasn't been explored much. And I sort of feel that it might be more important than we think. Okay, so that's really all I said about that. Let's have questions now.
Great. You get some protected topological numbers then?
Yes, yes,
Other loops?
exactly, exactly.
So is there a way to like tie two loops together that makes them like put it topological numbers?
I think the answer to that is yes, but I'm not, nature couldn't do it because of, yeah. Mm-hmm.
So the
Okay.
slot, these are for like, so if you take like the average plane, you sort of cut through it and check if you have twist or ±1 defects, or is this
Yep.
for specific or like on average for everything, or like if you have one loop, like what is this average?
It's averaging over lots of loops, all the possible loops you can have, and then a cross section all the way along all the loops. Yeah. You tend, though, in these systems, you tend to get loops with topological charge 0. I think I've got that right. Yeah. Yeah.
Talk a lot about, the is it obvious why the pop-up and second and then in that sort of chance? Or how is it exposed?
They pop up, well, what you have to do to get them to pop up is you have to overcome the elastic energy. Yep. because you have to basically create these nasty distortions. So that means that they tend to occur on places where you already have quite large elastic distortions. And those tend to be places, if you start with an instability, right? So you've got an instability which starts off being pretty much sinusoidal. What happens is that it sharpens up. So you get pneumatic regions with regions where you switch direction of the director, pneumatic regions with sort of walls where the director switches. And it's on those walls that the topological defects tend to occur. And that's because that's a place which already has some elastic energy, which is already a bit miserable. So it might as well form defects. Yeah. So it's an activated process. There is some very recent work. Okay, very recent. I'm not sure I know what I'm talking about here, but I think it's going to be interesting, which says that, and it's from Amin Mohammadi's group and Tyler Shendrock, I think. I'm not even quite sure if I can look it up. And what they've done is they've looked at an active system in 2 dimensions, and they've plotted out the lines where the vorticity is equal to the strain flow. So that omega equals E. So you get this sort of picture of lines which is evolving in time and where vorticity equals strain. And what they say is that the +1/2 defects follow these lines really very accurately in simulations. And I asked them why, and they said they didn't know. All right, -1/2 don't, +1/2 do. And that's one of the reasons why I think you can't think of defects as isolated things. They seem to be very slave to the underlying flow field. So that's a big question. I hope I've explained that right, but that's a new thought about how this thing works, which is really very interesting, I think. Yeah.
I wanted to know where at the start you showed us how there are processes to microscopy cooling and pushing.
Yes.
Is there any idea of how the density appears of these processes in the
I think they would probably make the defects slightly shorter or bigger, but not very much. I mean, it would be a small quantitative difference, but not a qualitative difference. But again, this is the question, I'm sort of washing all this out in this coarse grain picture. Yep. Yep. We should not think of it in terms of Kolmogorov scaling. Okay, people have tried to see if this turbulence is anything like inertial turbulence. And turbulence is a bad word. It's probably my fault. Because to me, turbulence means something chaotic, whereas to the experts, turbulence means inertial turbulence with Kolmogorov scaling. People have looked for Kolmogorov scaling in this, and there isn't any. And that makes sense, because there you pump in energy at large length scales and it cascades down. Here you pump in energy locally with all the little pneumatogens, and there is no transfer. People have looked, no transfer between scales. Completely different things, yeah. Yeah, sorry, it's a bad word. Although I must say, I mean, turbulence doesn't have to mean inertial turbulence, if you ask me, but yeah.
So as the Navier-Stokes equation had activity that I turned up the Reynolds number, I got some high Reynolds number where there was real turbulence with this. It's like inertial turbulence and active turbulence, the interplay between them, will that change anything?
You couldn't have active turbulence in straight Navier-Stokes because you need this pneumatic order parameter, okay? But you could certainly turn up the Reynolds number here. People have done that, but as far as I'm aware, nowhere near where you'd see real turbulence. It's an interesting question, but numerically it'd be horrible. Really hard to do. Yeah. Okay, good. Thank you, everybody. Thank you very much for the questions. I'll have one more question and then we should have coffee. See you tomorrow. Yeah, that's right. So what we'll do tomorrow is we'll start with an actual example of these active pneumatics in practice, which is a sort of researchy bit, which I put in. And then we'll talk about the details of active turbulence, answering questions like that. Okay, thank you.